Alright, in this video, what we're going to talk about is Chapter 7. And before we get into the details about Chapter 7 and start looking at some of these definitions that we have down here at the bottom of the page and continue with some of the details on the next couple pages, let's first start off with a discussion about the overarching picture about what we're going to do in Chapter 7 for estimation. So, if we start off with the picture that we began actually this entire semester with, then what we started off with was we said, suppose that we have some collection of things, right? It can be things, it can be people. If you remember back to the beginning of the semester, one of the first examples that I started off with was, I said, suppose that we were trying to figure out the average height of all students at UNC Charlotte. So let me first start off with a picture that's supposed to represent all students at UNC Charlotte. So here, this awesome picture right here. Let's just suppose that this picture represents all students at UNC Charlotte. And if we were trying to say something like what is the average height about all of these students, then what we would say is that this right here, this is our population. And if we were trying to figure out the average height of our population, we could go through and measure every single person in our population and then take the average of all those heights. And that then would be the average height of our entire population. But chances are we wouldn't want to go through and measure every single student at UNC Charlotte. So what we said instead was we would probably take some subset or some subgroup of this population. And if we take some subset or subgroup, so I'm going to say, suppose that we're just taking these individuals right here, this then would become our sample. Now, if we took a sample of people, and then we calculate out the average height of this sample of people, we could then say, hey, the average height of this sample of people, again, since we're dealing with the average, it would be our sample average, and the symbol that we use for our sample average is X bar. And again, X bar is one example of a statistic, right? Anything that you calculate out or any characteristic that comes from a sample, that's called a statistic. And we could use this statistic, the sample average, then to estimate what the population average is. So we could use this sample average then to estimate our population average. And remember that the symbol for our population average is given to us by mu. Mu is the symbol for our population average. And since our population average is something that we can calculate out or is a characteristic of our population, the definition that we know for this then is a parameter. And we've basically been dealing with this picture the entire semester. We've taken closer looks at different parts of it, but we've always said, hey, if we're trying to say something about a characteristic about a population, which is our entire group that we're interested in, we can take a sample of this population, which is just some subset of the population, calculate out that characteristic from that sample. So if we're looking at the average height, we could look at the average height of our sample. That's a statistic. Then we could use that statistic to estimate the population parameter. And then in Chapter 2, we started to look at the different characteristics that we could calculate out. We looked at the mean, the median, the mode, the standard deviation, and so on and so forth. In Chapter 3, then we started to look at different characteristics of probability, and we also in Chapter 4, then we started to look at looking at different sets. Maybe we're looking at the intersection of groups or the union of different groups. But we went through this different or this picture throughout the different chapters throughout the entire semester. Now what we're going to do is we're going to again look at a characteristic of this picture, but we're going to look at estimation. Now, obviously we're starting to give it away a little bit here since we're saying that we're going to use our sample statistic to estimate our population parameter. So we're already using the word estimate in it. But here's exactly where we're going to start to dive a little bit deeper into this picture. And that's this. Suppose that we were trying to figure out the average height of all students at UNC Charlotte. And then we took a sample of that group and we calculated out the average height of this sample, everybody in our sample. And maybe our samples are class, maybe our sample is everybody who's taking a statistics course this semester, whatever our sample might be. But it's definitely not everybody that's in the population. So we're not going to deal with a census. We're just going to deal with some subset of our population. If we calculate out the average height of our sample, I have no idea what X bar would be, but just for discussion purposes, let's say that the average height in our sample is 5 feet 7 inches. No idea if that's even close or not, but that's just going to be the guess that I have for what our X bar might come out to be. Well, chances are that the average height of people in our sample, 5'7", is going to be at least a little bit off of what the average height is of everybody in our population. It might be close, right? If we have a good sample, a good large representative sample, we're going to probably be pretty darn close. But say we only took the first 50 people that we see on campus. Well, chances are that even if we have 50 people, the sample average height is going to be at least a little bit off, right? Especially if you say this, right? Suppose you say, okay, I'm going to take a sample. I'm going to close my eyes. I'm going to walk out of Fretwell. And as soon as I walk out of Fretwell, I'm going to open up my eyes. And the first 50 people that I see, that's going to be my sample. So sure enough, you do it. You walk outside. You open up your eyes. As soon as you open up your eyes, right in front of you pulls up a bus full of the football team. And all the football players come off the bus, and all those guys are like huge. So you take the average height of that, and now if you say, hey, the average height comes out to be, 6'4" or something like that, chances are the average height of all students at UNC Charlotte is not 6'4", right? Now, suppose that you had maybe a little bit of a better sample, but chances are your sample average height is going to be at least a little bit off from what the average height is of all students at UNC Charlotte. So you can say this, all right, I know that this number is going to probably be off by at least a little bit, so let me give myself some wiggle room, right? Let me say, hey, I know 5'7" is probably close, but it's probably off by a little bit. So let me say that I think that the average height is 5'7", but let me say that I'm pretty sure that the average height is going to be somewhere between 5'5" and 5'9", right? So suppose that somebody says, "Hey, I'm trying to figure out what the average height is of all students at UNC Charlotte." You could then give that person the answer that I think that the average height is 5'7", but I'm pretty sure it's somewhere between 5'5" and 5'9". Well, what we just did here is we just gave ourselves a little bit of wiggle room. Gave ourselves a little bit of wiggle room below our estimate and gave ourselves a little bit of wiggle room above our estimate. Here, I just so happen to choose to add 2 inches to this side and to subtract 2 inches from this side, right? Again, I'm just pulling these numbers out of thin air just to give ourselves a little bit of a better idea of what this chapter is going to be dealing with. So, I said, I think the average height is 5'7", but I'm pretty sure it's somewhere between 5'5" and 5'9". Well, that statement is actually going to be the statement that we're going to break apart throughout Chapter 7. So let me say it one more time. I think that the average height is 5'7", but I'm pretty sure that the average height is somewhere between 5'5" and 5'9". Alright, because now what we have is we have a couple of components that are all kind of vague, and obviously whenever we're doing math and stats, vagueness is never a good thing. So let's try to point out where the vagueness is in that statement, and also where we're going to start to narrow things down and nail things down a little bit in this chapter. First is this. How did I determine to subtract 2 inches and to add 2 inches? Why didn't I subtract a half of an inch and add half of an inch? Or why didn't I subtract a foot and add a foot, right? If you're trying to say, hey, I'm trying to be really confident about my estimate, you could say, hey, I think the average height is 5'7", but I'm pretty sure it's somewhere between 2 feet and 10 feet, right? To which you would say, well, no, duh, the average height is somewhere between 2 feet and 10 feet. But what happens if somebody comes to you and says, hey, I think the average height is 5'7", but I'm really certain that the average height is from 5 feet 6.5 to 5 feet 7.5. Well, if that person's really darn certain about that little, just adding that little bit of wiggle room to each side, that person must be really, really confident about what they're doing. So how much we add to each side and how much we subtract from each side is definitely something that we're going to narrow down in this chapter. And I've been calling it our wiggle room, but the technical term that we're going to use for it is our margin of error. Margin of error. So the wiggle room that we're giving ourselves, the amount that we're adding to and subtracting from this statistic right here, that's what we're going to call our margin of error. So we're going to subtract our margin of error and we're going to add our margin of error. Now, this point right here, too, the statistic that we've calculated out, this 5'7" number that I'm using, this is what we're going to call our point estimate. Now, why is it called our point estimate? It's called our point estimate because if somebody comes to you and goes, just give me one number for the average height of students at UNC Charlotte. If they're just looking for one number, you would say, okay, I think it's 5'7". That's just one number, and you can think of this as being one number on a number line, or just one point on a number line. So just this one number, that's 1 point on the number line, so that's why we're going to call it our point estimate. However, once we subtract our margin of error and add our margin of error, now what we've done is we've created an interval of values in which we think that the average height of all students at UNC Charlotte is. So we're creating an interval somewhere between 5'5" and 5'9". So if somebody says, okay, give me a range or give me an interval of values that you think is going to contain the average height of all students at UNC Charlotte, you might say that the interval that you're going to give them is between 5'5" and 5'9". So therefore, this range or this interval, this is what we're going to call our interval estimate. So what we've done in previous chapters is we've calculated out a sample average before. So therefore, what we've done so far is we've come up with a point estimate. But now what we're going to do is we're going to figure out how big our margin of error needs to be in order to create our interval estimate. And now the last thing one of the last things that we're going to also say about this interval is how confident are you about this estimate, right? Like I said before, if you say, hey, I think that the average height of students is 5'7", but I'm really darn sure it's between 2 feet and 10 feet, now your confidence in your interval is super high. And it should be, right? I think it's really super certain that the average height of all students at UNC Charlotte is somewhere between 2 feet and 10 feet. So you should be really, really confident about that interval that you're giving. But also keep in mind that you're not really conveying a whole lot of information at all. Of course it's somewhere between 2 feet and 10 feet. So another thing that we're going to talk about is our confidence in this interval estimate, and therefore also how much information we're actually conveying with this interval estimate that we're coming up with. So therefore, another term that you might hear for interval estimate is that we're creating a confidence interval. It's called a confidence interval because not just are we creating an interval, but we're also going to specify a certain level of confidence in that interval that we're creating. And this is basically what Chapter 7 is all about, is creating this confidence interval and also describing how we're creating this interval. How are we creating our margin of error? What is our point estimate? And so on and so forth. And all that we're using this then is to say, giving an interval around our statistic and stating a certain level of confidence that our parameter is going to be within our estimate that we're creating. All right, so this is the overarching picture. If we now glance down here to some of the definitions that we have, I think that these definitions should be relatively clear from what we have up here in the picture. First off is this, our margin of error. It says that here we're going to use this symbol capital E for our margin of error. So another thing that we can add up here then is to say that our margin of error, here we're subtracting E, and over here we're adding E to it. If we're subtracting our margin of error and adding our margin of error, and if we're going to use E for our margin of error, then you can also say that here we're subtracting E, and here we're adding E. So we're going to take our point estimate and subtract E, and take our point estimate and add E to it in order to create our interval. So here then, the margin of error, capital E, is a number added to and subtracted from the point estimate to produce the interval estimate. All right, well that makes sense. Take our point estimate, add the margin of error to it, subtract the margin of error from it in order to come up with our interval estimate. Our confidence interval is an interval with endpoints x bar plus or minus E, which we have. Here we have x bar. Over here we have plus E, which is our 5'9". And here we have x bar minus E, which is 5'5". So we have our interval from 5'5" to 5'9". Those are the endpoints. Computed from sampled data, which we're doing since we're using our x bar, in such a way that a specified proportion of all intervals constructed by this process will contain the parameter of interest. So here, this last portion right here, this is something that I'm going to discuss a little bit on the next page. I'm going to draw another picture of that. But just keep in mind that our confidence interval is going to be the same thing as our interval estimate, as long as we're looking at constructing these intervals using a certain process. Always using a certain process. And here now we also have our confidence level. The confidence level is the proportion of confidence intervals which, if under repeated random sampling were always constructed according to the process below, would contain the parameter of interest. All right. If this right here, if the confidence level isn't super clear yet, there's two things that you should keep in mind. First thing is this. We've already talked about our confidence level in our interval. Again, if we had a huge margin of error, so we went from 2 feet to 10 feet, our confidence in that interval should be super high, but we're not conveying a whole lot of information. So we've touched on the concept of confidence so far. The second thing that you should keep in mind is this thing right here that says it's super, super, super important. And that is the formula that we're going to use. You can think of this as a formula that we're going to use. The formula that we're going to use for the confidence level is 1 minus alpha. That's super important for you to remember. So, anytime that I ask you, what's our formula for the confidence level? You should say that it's 1 minus alpha. So, confidence level is given to us by 1 minus alpha. Alright, so I'm hoping that this picture right here gives us a good overarching picture of what we're going to do in Chapter 7. I articulated it a little bit more again in these 2 paragraphs right here. You can read through those 2 paragraphs by yourself. And now here we're starting to talk about some of these definitions. But let's try to clear up these last 2 definitions a little bit more. And for that, we're going to come here to the next page of notes. So here, I'll just take this away since we can't really see that. Alright. So what are these last 2 definitions really meaning? So let's start off with this. Suppose I have a normal distribution, right? And our normal distribution is simply just a bell-shaped and symmetric distribution that looks something like this. All right. Now, suppose I do this, right? Suppose that I say that this right here is where the average is, right? Since it's bell-shaped and symmetric, we know that that's not just the average, but from symmetry, we also know that this right here is also the median. And now, because I said that this was going to be our normal distribution, then this right here is also equal to the mode, but I'll just use a symbol for the average. Alright, suppose I went 2 standard deviations above this mean. And here, just for the sake of discussion purposes, I'll say that the standard deviations that I'm going above is a population. So suppose that I'm going 2 standard deviations above the mean, and suppose that I'm going 2 standard deviations below the mean. First off, then, using the empirical rule, try to remember back to the empirical rule. If you go 2 standard deviations above the mean, and you go 2 standard deviations below the mean, what percentage of our data do we have then between these 2 cutoffs? So the percentage is 95%, right? If you go, right, remember those 3 percentages from the empirical rule, 68%, 95%, 99.7%. 68, 95, 99.7. So therefore, the empirical rule tells us if we go 2 standard deviations above and 2 standard deviations below, then in between these 2 cutoffs, we should have 95% of our distribution, or just of our data. Alright, so exactly what does that mean? Remember back when we were doing the example of how many times in a month do you call your mother, right? And that was our first discussion about distributions, and then I took those, I collected those pieces of paper from everybody, and then I went through those one by one, and I plotted those dots. And then when I plotted those dots, that's when I said, okay, it's going to kind of start to look a little bit like Connect 4, right? So imagine that these dots in here that I'm drawing, those are the same dots. And now if you drew all those dots in here, it would look something like this, right? And I know I'm getting a little bit sloppy with them a little bit, but here, roughly speaking like that, right? Now, suppose that we were dealing with a continuous random variable. Here we would have a smooth line, continuous line right here in this example since it's the normal distribution. But the reason why I'm reminding you of this is this. If I go 2 standard deviations above the mean to this cutoff and 2 standard deviations below the mean to this cutoff, that means then that 95% of my dots in here should be in between these two cutoffs. Right? 95% of the dots then should be in between these two cutoffs. Suppose that I took any one of these dots in here. It doesn't really matter which one you take. But suppose I just took this one right here. I'll make it a little bit bigger. If from this dot I made an interval, and this interval was also 2 standard deviations to one side, and 2 standard deviations to the other side. I got a little bit sloppy there. 2 standard deviations to the other side. So you can think of this right here as being a sigma, this right here as being a sigma, this one here is a sigma, and this is sigma. So that this distance right here, from this dot that I chose to the end of an interval, is the same distance as mu is from here to where this 95% cutoff is. Then does everybody agree then that the value of mu should be somewhere inside of this interval? Right? So again, if I picked one of these dots in the 95% range right here, any one of the dots, I just happen to take this one right here. If I created an interval around this dot, from here to here, and this interval was the same length on each side as we have down here, then this interval is going to extend down past to where the value of mu is, right? Think of it as a number line that goes from here to here. Here you have some value. This value is definitely going to be a value that's contained within the interval from here to here. I could do this for another spot. I could say, let me choose this dot right here instead. The exact same concept applies. If I create an interval around this dot, and again this interval was the same length on each side as I have down here, then this interval that I'm creating too has to contain the value that's mu. However, on the other hand, if I take one of these dots over here that's now outside of the 95% range, and I again create an interval around it, and this interval again has the same length on each side as this 95% one, right? So this right here is a sigma, and this is a sigma, so it's 2 sigmas above and 2 sigmas below. Now this interval that I'm creating will not contain the value that is mu, right? Again, think about this as a number line. This interval on the number line does not extend all the way up to mu, so therefore whatever value this is right here, this interval is not going to be, this interval right here is not going to contain the value mu. So therefore, since 95% of our dots are in between these two cutoffs, that means that 95% of the intervals that I create, like I did right here where I'm adding and subtracting 2 mu's from each side, only the intervals that I create in this 95% range right here will contain the value mu. So therefore, 95% of the intervals that I create, like this, will contain mu. And the other 5% that are either to the right of this 95% range or to the left of this 95% range, these dots over here, if I create an interval around it, those intervals will not contain mu. So therefore, 95% of the intervals that I create in this way will contain mu. And therefore, if I asked you this, I'm going to say, hey, I'm going to pick one of these dots in here, and I'm not going to tell you which dot it is. But the dot that I pick, to the left of it, I'm going to add 2 mu to it. And to the left of it, I'm going to add 2 sigma to it. And to the left, I'm going to subtract 2 sigma from it. What is this interval going to contain mu or not? Well, the only thing that you can say is that you're 95% confident that it would contain mu, since 95% of the intervals that you create would be such that they would contain the value of mu. So therefore, this 95% right here, this is what we're going to call our confidence level. Again, let me run through that scenario one more time so it makes really a lot of sense why we're calling it our confidence level. If I picked one of these dots anywhere in here, and I didn't tell you which dot I picked, but I told you that I was going to subtract 2 sigma from it, and I was going to add 2 sigma to it to create my interval, and I then asked you, does that interval contain mu in it? You could say yes, but you would only be 95% sure that it does, because only 95% of the intervals that you create like that would contain mu in it. If I happen to pick a dot either over here or all the way over here, those intervals would not contain mu in it. So therefore, this 95% is not just the percentage of intervals that would contain mu, but this is also going to be how confident you are that if you pick an interval at random, that interval would contain mu. So therefore, since this is our confidence level, again, what's our formula for confidence level? So that was something that's really, really important for you to remember, as on the definitions on the previous page. It's 1 minus alpha. So let's see why the formula of 1 minus alpha makes sense. First off, let me ask you this. If in between these two cutoffs we have 95% of our data, and that's given to us by 1 minus alpha, if you were to express this area in this graph right here, so from the right of this cutoff and down, how could you express the area in this tail right here, the one that I just shaded in darker, how could you express that in terms of alpha? So take a minute and think about that for yourself, right? As always, if you ever want to pause this video and rewind it and listen to something again, or if I ask you a question and you don't want to listen to the answer right away, you want to try to figure out for yourself for a minute, I'm going to ask you questions just like I was talking to you in class. So you can pause the video, try to think it through, and then once you think you have an answer, you can restart the video to see if you get it right. So let me ask you the question again. Saying that if in between these two cutoffs, which is 95%, if that is given to us by 1 minus alpha, right? So 95% is the same thing as 1 minus alpha, or is equal to 1 minus alpha. If you were trying to express this dark shaded region right here in terms of alpha, what would that expression be? So let's think about it. If this right here is 95%, and we have 95% is the same thing as 0.95. If that is our confidence level, and our confidence level is the same thing as 1 minus alpha, then we have this right here. If I wanted to solve for alpha, I could add alpha to both sides and then subtract 0.95 from both sides. So then I would get that alpha is equal to 0.05. So one of the things that I'm going to ask you repeatedly throughout this chapter, and probably also into the next chapter as well, definitely into the next chapter as well, is that if this is our confidence level, if 95% is our confidence level, whatever is left over to 100, that's going to be what alpha is equal to. So I'm going to say, okay, if our confidence level is 95%, how big is alpha? And alpha is just going to be what's left over to 100%. So in this case, it's 5%. But what's left over outside of this 95% range is both what's to the left of here and what's to the right of here. Since it's symmetric, we know that the amount that's over here is going to be the same as the amount that's over here. So therefore, if what's ever left over is alpha, here we're going to have alpha divided by 2. And over here in this tail, we're also going to have alpha divided by 2. Or 0.025, which is 2.5%. And here, again, this is going to be 2.5%. So therefore, 2.5% and 95% and 2.5% now equals 100%. So therefore, if in here we have 1 minus alpha, in this tail we need to have alpha divided by 2, and in this tail we need to have alpha divided by 2. So that we can have then half of alpha, 1 minus alpha, and half of alpha, this being equal to 100% of our distribution. All right. So why is this so important? Well, one of the things that we're going to look at a lot in this chapter is this. We're going to start looking at these cutoffs right here. Now, in this example, I chose 95% to keep it simple because we could use the 95% from the empirical rule, but I could use anything for our confidence level. I could use 68%, I could use 62%, I could use 23%, I could use 99%. I could choose any confidence level that I want. And based off of the confidence level that I want, that's going to be the percentage then that I'm going to have between these two cutoffs. Or again, the number of dots, or the percentage of dots rather, the percentage of dots that are going to be in between these two cutoffs. So this number right here, this is going to change a whole lot just from example to example that we do. But what we're always going to be interested in is we're always going to be interested in this cutoff and this cutoff. And what we've always been doing is think back to what we did in chapter 5 and in chapter 6. One of the things that we always try to boil those problems down to were z values. So we're going to try to again figure out, and since we're dealing here with a normal distribution, we can have these z values. We're going to be interested in these z values right here. And because now we're dealing with these z values and we're also looking at these alphas, the notation that we're going to use for these is z sub alpha divided by 2. And I'm hoping now that it makes a little bit of sense where these alpha divided by 2, this alpha divided by 2 notation is coming from. Because we're going to figure out a z value that corresponds to us having alpha divided by 2 in one of these tails. Now, clearly, since this z value is above the mean, this is going to be a positive z value. And since this z value is below the mean, this is going to be a negative z value. But right now, I'm trying to make sure that everybody's clear with the fact of how did we get this alpha divided by 2. And it's really just a notation thing to signify the fact that we have alpha divided by 2 in these tails. Alright. So now, here what we have is we have, again, a really similar picture to what we just created above, where we have that our confidence is given to us by, our confidence level is given to us by 1 minus alpha. A notation that you're going to see a lot for this, especially in your textbook, is 100 times 1 minus alpha percent. So here, if I told you that we use this problem like we had above here, right? A lot of times what you're going to see is that problems are going to tell you what alpha is. Some problems are going to tell you what your confidence level is. Either way, I'm hoping that you're seeing that regardless if they're going to give you your confidence level or if they tell you what alpha is, you can get one from the other one. Notation that you're going to see here sometimes is this, 100 times 1 minus alpha percent. Another way of saying that is if they tell you that alpha, will stick with the same number, is 5%, and you want to figure out your confidence level, well, what you would do then is you would plug that 0.05 into this formula. This is not something that you need to memorize. Right? I'm just showing you that that these two things are saying the exact same thing. Then this right here is going to be 0.95. And if you take 0.95 times 100, you get 95%. And 95% is our confidence. So you can go from alpha to the confidence. They're going to use this right here a lot. But just keep in mind that all that this is saying is that if our confidence level is 95%, then alpha is just whatever is left over to 100%. Here I wrote it as a decimal place, but you could just as easily write it as a percentage as 5%. Now, while we're at it, and this is going to be a vocabulary word that we're going to use a lot in the next section, or in the next chapter, in chapter 8, another term that's synonymous for alpha is our significance level. Significance level. Our significance level is just another synonymous term for alpha. Alright. So here's a little bit of a nicer picture of exactly these z's. Right, whenever this is a distribution, a bell-shaped symmetric distribution, the normal distribution, we know that the z value of the mean is going to be equal to 0. Inside here, we're going to have 1 minus alpha, which is just our confidence level. So therefore, over here, we're going to have alpha divided by 2, and over here, we're going to have alpha divided by 2. Alright, so if we backtrack and now look at our definitions, the ones that we looked at earlier, I'm hoping that for confidence interval and confidence level, it's going to make more sense. Again, let's read through them. For the confidence interval, it's an interval with endpoints x bar plus or minus e, and that should have been straightforward because that's, again, plus or minus our margin of error. Computed from sample data, which should make sense since we're using x bar right here, and x bar is our sample statistic. In such a way, and now this is what I'm hoping makes more sense now, in such a way that a specified proportion of all intervals constructed, here that specified proportion of intervals constructed was 95%. So 95% is the proportion of intervals that are constructed by this process will contain the parameter of interest. So 95% of our intervals that we constructed in this way will contain our parameter of interest, and here our parameter of interest was mu. So 95% of the intervals that we constructed, and the process that we used in this example was adding 2 standard deviations above and 2 standard deviations below. 95% of those intervals contained mu. Then our confidence level is the proportion, right? Confidence level is this 95%. The confidence level is the proportion of intervals, confidence intervals, which if under repeated random sampling were always constructed according to the process below, which is the one we just got done talking about, would contain the parameter of interest. So here it's just talking about the intervals that we're constructing. Here it's talking about our levels of confidence in those intervals. And again, where our confidence level is equal to 1 minus alpha. Alright. So that was a rather long overview of not only the big picture from Chapter 7, but also some of the definitions and some of the notation that we're going to use going forward. Before we get into some, actually doing some numerical problems, let's take a look. Now we're getting into section 7.1, right? So this other part that we talked about was really just like the prelude to us doing this and looking at the overarching picture. Now we're talking about section 7.1. And section 7.1 talks about large samples. So, since we're talking about large samples, if you remember back to our discussion about the central limit theorem, there the general rule that we had for large samples when we were looking at the mean was, right, and here we're looking at the population mean. In order for a sample to be large, when we're looking at the mean, is that our sample size, which is given to us by little n, needs to be greater than or equal to 30. So first off, this first topic that we're going to talk about is what happens if what we're trying to estimate is the population mean whenever our sample sizes are greater than or equal to 30. So that's why it's called the large sample estimation of a population mean. First off is this. We really have two different scenarios. One is whenever we know what the population standard deviation sigma is, and one is whenever we don't know what the population standard deviation sigma is. So in one case we know sigma, in one case we don't. If we're trying to create a confidence interval, then just like we did before, we're going to start off with our sample statistic, and we're going to add and subtract our margin of error, right? So again, we're going to take our sample statistic, and we're going to add and subtract our margin of error. So here the formula for that is to take our sample statistic and add and subtract this portion right here. Well, then therefore, this portion right here, this is just the same thing as our margin of error E. So you can think of this as, since we're taking our sample statistic and we're adding E to it and we're subtracting E from it, you can think of this formula right here as being nothing more than x bar plus or minus E. So then therefore, a more specific description of the formula for E, for our margin of error, is this right here. But if you take a close look at this, inside this portion right here, we have sigma in it. So if we want to have sigma in this formula, we need to know what sigma is. That's why we have it in our formula. If we don't know what sigma is, and we come down here then, well, that's why here in this formula we don't have sigma. Instead we have S. Again, try to remember for yourself, what does the symbol S stand for? S stands for the sample standard deviation. So therefore, if we don't know the population standard deviation, we're going to use our sample standard deviation S instead. Alright, so therefore we still have these z sub alpha divided by 2's. Those are the ones that we talked about up here above, the z sub alpha divided by 2's. And we're going to multiply that by sigma divided by the square root of n. Again, where little n is our sample size. And here in the second formula for large sample estimation of the population mean is when we don't know sigma. So now we're still going to have all the rest of the formula the same, but instead of using sigma, we're going to use our sample standard deviation S instead. All that this right here says is exactly what I stated up here in this problem. Here it just says that this upper cutoff is x bar plus e, and here it says that this lower cutoff is x bar minus e. So therefore, if you were trying to create an interval, you would say it would go from x bar minus e to x bar plus e. And that's what it says right here, where e is our margin of error, capital E is our margin of error, where what we're adding to and subtracting from is our margin of error, so it's given to us by either z sub alpha divided by 2 times sigma divided by the square root of n if we know sigma, or if we don't know sigma, then e is equal to z sub alpha divided by 2 times s divided by the square root of n. Alright, so let's go ahead and try to practice finding some of these z sub alpha divided by 2's. In chapter 5, we practiced a whole lot how to find z values. And the reason why we practiced it a whole lot then was, like I said, a lot of the stuff that we're going to do for the rest of the semester is going to rely on you knowing how to find z values. Here we're going to still find z values, but they're slightly different. There's z values for alpha divided by 2. So we're going to have to switch things up just a tiny little bit. But we're going to go through a couple of examples. So it says here, find the number z sub alpha divided by 2 needed in the construction of the confidence interval. So here, all that this is saying is that, hey, eventually, what we're going to do is we're going to use z values like these whenever we construct confidence intervals. But before we get all the way to constructing confidence intervals, let's first practice finding these z sub alphas, since we know that that's a component of our confidence intervals. So let's do A together. It says our confidence level is 95%. Well, this one should seem really, really familiar to you. What I'm going to do, like I usually do, is I'm going to start it off with a picture. And since we're looking up z values, we know that we're dealing with a normal distribution. And our confidence level is 95%. So just like I did before, I'm going to have our confidence level between these two cutoffs. And here I'm going to say that this is 95%. This is really similar to the example that we started off with at the beginning. So therefore, if we have 95% in here, then how big is alpha? Well, if 95% is our confidence level, then 95% is equal to 1 minus alpha. So therefore, all of alpha is equal to 5%, or simply just 0.05. So whatever is left over is equal to alpha. So therefore, we're going to put half of that 0.05 over here. We're only going to put 2.5% over here and 2.5% over here. Remember that it has to be a symmetric distribution. So the same amount that has to go over here, that goes over here. And in order for it to be 100%, right, 2.5% plus 95% plus 2.5% is 100%. So therefore, over here we have alpha divided by 2. And over here we have alpha divided by 2, since alpha is equal to 5%. So what we're looking for is we're looking for z sub alpha divided by 2. So keep in mind here this, and this is something that's important and maybe a little bit unique to my notation for this stuff. And my notation for this stuff is that we're always going to consider z sub alpha divided by 2. Whenever I talk about z sub alpha divided by 2 in my classes, I'm always going to think about this number as being a positive number, right? So keep in mind here that this, and the reason why I'm pointing it out is the z value that's above the mean is always a positive value, and the z value that's below the mean is always a negative value. But whenever I ask you questions, just for the ease of conversation, when we talk about z sub alpha divided by 2, conceptually, I'm always going to pretend like we're talking about a positive value. So what I'm going to say then is here we're going to have, keep in mind that this right here is going to be a positive z value, and this one here is going to be a negative z value. But later on when we're dealing with the formulas, and I ask you for the z value, I'm going to be looking for the positive z value. All right, so let's do it. We're still trying to figure out what these z values are. So therefore, we know that this z value corresponds to this tail where there is just 2.5% in that tail. So take a minute for yourself and see if you can find the z value that corresponds to having 2.5% in that tail. And while you guys are trying to figure that out, I'm going to admit that I'm completely unprepared and I don't have a z table in front of me. So I had to go grab one real quick. All right. Whew. Back. All right, so let's do it. We're trying to figure out the z value that corresponds to having 2.5% here. So therefore, since we're in the left tail of our distribution, we're going to go hunting for 2.5% inside here. And if we go hunting for 2.5%, we're going to find that 2.5% right here, 0.025. 0.025 is the same thing as 2.5%. Now, if we follow this outwards, we're going to have that it's negative 1.96. So the z value that's over here is negative 1.96. Now, I'm hoping that at this point that you're comfortable with the fact that since we're equidistant away from the mean for these cutoffs, and if this is a z value of negative 1.96, then this right here should be a z value of positive 1.96. If you're not too sure in that, keep in mind that if we have 2.5% right here in this upper tail, then from here on down, we should have 97.5% of our distribution, right? So 97.5% is from here on down. So you could also go looking for 97.5%, but 97.5% would again be right here. And sure enough, it's going to lead you to a positive 1.96 for your z value. Again, keep in mind that inside the body of this table, these are percentages, and your z values are just what's in the first row or in the first column. Right? First column is the z value down to 1 decimal place. The first row then gives us our second decimal place for our z values. So here we have it. If we're trying to look up a z value, we have that z value is equal to 1.96. Like I said, I'm always going to default to the positive z value for our discussions. Alright, try to pause the video and do these next three by yourself. We're going to try to find the z value, z sub alpha divided by 2. But now we're going to change our confidence level. So we're changing the percentage that we have inside here in the middle. So try to do these couple by yourself. Alright, so here then, if we start this off the exact same way, since we're looking for z values, we know that we're going to use a bell-shaped and symmetric distribution. Here now, instead of having 95% in here we want to have a confidence level of 80%. And again, our confidence level is given to us by 1 minus alpha. So therefore, if our confidence level is 80%, then alpha is going to be whatever is left over to 100%. So alpha is going to be 20%, which is just the same thing as 0.20. Since that's everything that's left over, that includes both what's to the left of this cutoff and what's to the right of this cutoff and to the left of this cutoff. So therefore, over here we're going to have 10%, and over here we're going to have 10%. So we have 10 plus 80 plus 10 is 100%. Since alpha is 20%, this is just the same thing as alpha divided by 2, or half of alpha. That's why we're calling these cutoffs z sub alpha divided by 2, knowing full well that this is a positive z value and this is a negative z value. So what we're looking for is a z value that corresponds to having 10% in this left tail right here. So if we're looking for the z value that has 10% in it, again, we're to the right of the mean, so we're going to go to the back side of our z table. And now we're going to go hunting for 0.10 or 10%. If you go hunting for 0.10, the closest that we can get to is right here. 0.1003. Which if we follow, right, this is our percentage. If we follow it outwards, we get that it's a z value of negative 1.28. Negative 1.28. That's as close as we can get to 0.10 or 10%. So therefore, over here, we have that it's negative 1.28. And therefore, over here, we have that it's 1.28. So therefore, we're going to say that our z sub alpha divided by 2 is going to be 1.28. So let me point something out here, and this is going to be really, really important for the next section, section 7.2. But just to highlight a little bit of what we're going to do here, this is a perfect example. What we were looking for is 10% or 0.1. The value that we ended up looking up in our table was 0.1003. So we're off by a tiny little bit. It's not exactly the value that we wanted. So therefore, we're going to estimate that our z value, right here, z sub alpha divided by 2, we're going to estimate that our z value was 1.28. Or if we're still going along with this right here, we would look up the value of negative 1.28. Now, if we wanted to be more accurate, and instead of looking at 0.1003, if we wanted to look up 0.10, then, right, 0.100000, we could find a z value that's a little bit more accurate than this one. To be a little bit more specific about it, you can see that if this is 0.1003, the direction that we want to go is we want to go somewhere in between these two values, 0.1003 and 0.0985. So really what we're going to be looking for is we're looking for a z value that's somewhere between 1.28 and 1.29. We want to have some z value that's somewhere in between here, where it's going to be a little bit closer to 1.28 than it is to 1.29, right? We only want to get a little bit away from this, but not quite all the way to 1.29. All right. So all I'm doing is I'm foreshadowing the fact here that in the next section, we're going to be able to state this a little bit more accurately. We're actually going to be able to go down to 3 decimal places. But for right now, if we're just trying to go to 2 decimal places on our z value, the closest one that we can get is 1.28. Alright. For this next one now, our confidence level is 90%. Again, I'm going to do the exact same thing like we have been in the previous 2 examples. between these two cutoffs now, we want to have 90% as our confidence level. Our confidence level, again, is given to us by 1 minus alpha. So therefore, over here we have 5%, and over here we have 5%. So therefore, alpha is going to be whatever is left over between 90% and 100%. So alpha is going to be 10% or 0.1. So since this is just 5%, this is going to be half of alpha, and this is half of alpha, which again I'm hoping solidifies the fact of why we're calling these cutoffs z sub alpha divided by 2. So again, if we're trying to hunt for a percentage in our table, we're going to be looking for a percentage that's 5% or 0.05. Again, the percentages in our z table are what's in this body of our table right here. We're looking for 0.05, and if we look for 0.05, we're going to see that 0.05 is exactly in between these two values right here, which is negative 1.64 and negative 1.65. But now let's take a really, really close look at this. We're in between z values of negative 1.64 and negative 1.65. We're looking for 0.05. Note here that 0.05 is exactly in the middle between these two values. Right? We're as far away from 0.05 here as we are right here. So therefore, what we could use is we could use the z value here for negative 1.64. We could just as accurately use the z value of negative 1.65. So we could say that z sub alpha divided by 2 is equal to negative 1.64, or we could simply just say that it's equal to negative 1.65. And the answer choices that you're going to have in this class are never going to be so close that you're going to get it right if you use one of those numbers, and you're going to get it wrong if you use the other one, right? They're never going to be that close. But keep in mind here that since the z value that we're looking for is really right between these two z values, the most accurate that we could get is negative 1.645. Right? Because negative 1.645 is right in between negative 1.64 and negative 1.65. So, just as we figured out this third decimal place, we're going to use a different table in our next section to also figure out this third decimal place like I was talking about before. Now, last but not least, like I said, the way that I'm going to discuss these things is that our z sub alpha divided by 2's, I'm always going to discuss them as if they're positive z values. So therefore, the z sub alpha divided by 2 that I'm going to use for this is positive 1.645. Again, until we get to that other table, your answer choices would be fine if you just use 1.64 or 1.65. But the way that the answer choices are actually going to be calculated, right, the correct answer choice is I'm going to use 1.645. So if your answer is a little bit off, that's probably why, unless you're using the value of 1.645 for this. Alright, then the last example right here is for a 99% confidence level. And for a 99% confidence level, we're going to have the exact same thing since we're using z values. We have this bell-shaped and symmetric distribution. Here we're going to have 99%, which is again given to us by 1 minus alpha. So therefore alpha is whatever is left over to 100%, which is 1%, or the same thing as 0.01. If in here we have 99%, then over here we're going to have half of a percent, and over here we're going to have 0.5%, in order for our entire graph to be equal to 100%. So therefore this is the same thing as alpha divided by 2, or half of alpha. That's why, again, and it's probably going to be the last time that I'm going to say this, but I'm hoping that that solidifies why we're calling this z sub alpha divided by 2. Because here in the tails we are only considering having half of alpha. So again, if you're trying to figure out what this z sub alpha divided by 2 is, here in this tail we have 0.5%, which is just the same thing as 0.005. Right, 0.5% is 0.005. So again, now in our table we're going to go hunting for 0.005. And the closest that we can get to it is for negative 2.57. Negative 2.57. You can see here that negative 2.57 and negative 2.58 again are equidistant. Using this table, are equidistant away from 0.005. So again, you could either use a z value, z sub alpha divided by 2 of 2.57 or 2.58. But to be more accurate, what z sub alpha divided by 2 could you use? If you're saying 2.575, then you're on the exact right track. Because 0.005 is the same distance between these two. Same distance from this one as it is from this one. So therefore you could say that you're going to use 2.575, which is halfway in between 2.57 and 2.58. Now, really, mathematically speaking, this is what we're going to see in our next table, and also why we need a table is this. This is going back to a little bit of the discussion that we had in Chapter 5. Really, this is not 2.575, but it's really more accurately 2.576. Now, again, keep in mind that back in our discussion in Chapter 5 was, if you remember, just really quickly, I asked you if we went one standard deviation above the mean and one standard deviation below the mean for our normal distribution, then here, using the empirical rule, we could say that here we had 34% and here we had 34%, for a total of 68% if we go one standard deviation above the mean and one standard deviation below the mean. So this would be mu plus sigma, and this is mu minus sigma. But if you remember from our discussion, I said, what happens if I take this sliver right here and I only wanted to go half of a standard deviation above? Right? If I took that sliver right here and I blow it up, so if I say that this right here is my 34% sliver, if I go halfway up, I think everybody will agree then that this half over here is smaller than this half over here. So if this is just half of a sigma, and this right here is half of a sigma, we can't say that this right here has 17% in it, and that this right here has 17% in it. We said that this is not true. So we also can't just say that we can go half of the percentage up and half the percentage down. The reason why this is not 5.575, but is in fact 5.576, is back to this whole concept right here. So again, if this is a little bit foggy for you, go back to the discussion that we had in Chapter 5 for this, and I'm hoping that that becomes a little bit more accurate. But also, this is also highlighting why we need to have a different table if we were trying to get down to the third decimal place. But that's going to be in the next section. For now, let's wrap this up and say that for the time being, that this is 2.5 2.576. But again, as long as you're good to go with how to get down to the second decimal place for 2.57 or 2.58, then you're good to go. But we'll pick it up here in the next section, which is also going to be the next video.